Hello and welcome to this lesson for OCR A-Level Physics in the module of the Newtonian World and Astrophysics in the topic of oscillations and on the concept of simple harmonic oscillators. So if we've been successful and we've learnt in today's lesson, we should be able to describe the characteristics of simple harmonic motion, explain the conditions needed for simple harmonic motion, and calculate properties of simple harmonic oscillators. So in today's lesson, we're going to be looking at the following parts of the specification: 5.3.1 Simple harmonic oscillations. Now, objects can carry out oscillating motion based on Newton's laws of motion. So we can see on the screen now an example of oscillating motion. But what is the definition of oscillating motion? Well, oscillating motion is when an object moves either side of an equilibrium position in the same plane. Now, the equilibrium position will be the midpoint of the motion. The equilibrium position is the position in the motion where the object will reside under no force. The equilibrium position is the position in the motion where the object wishes to reside, because the equilibrium position is the position in the motion where the object is in its lowest potential energy state. Now, an oscillating object will always wish to return to equilibrium. So, as we know, oscillating objects do not stay at equilibrium because they have inertia in their motion. So oscillating motion is the motion back and forth about a fixed point in a straight line in the same plane. It is the repetitive motion along one plane of motion about an equilibrium position. Now, all oscillators share similar characteristics. In each case, the object starts in the equilibrium position, a force is then applied to the object, displacing it, and it begins to oscillate. So an example of oscillating motion can be a swing. An example of oscillating motion can be a rocking horse. An example of oscillating motion can be a clock. An example of oscillating motion can be Newton's cradle. An example of oscillating motion can be a pendulum. And an example of oscillating motion can be the chandeliers moving back and forth in Pisa Cathedral. Now, each of these systems is demonstrating simple harmonic motion, which is a special type of oscillating motion. Now, what is the difference between oscillating motion and simple harmonic motion, and what is so special about it? Well, simple harmonic motion is the special case of oscillating motion caused by a resulting force that repeatedly acts to restore a moving object to its equilibrium position. So, for example, a metronome, which is a doubly weighted pendulum, and a pendulum have simple harmonic motion because there is always a force acting towards the centre of oscillation. So, as we've said, simple harmonic motion is the oscillating motion produced by a force acting on the object to move it back to the equilibrium position of the motion, and this is called the restoring force. Now, the restoring force is always acting in the opposite direction to the movement as it wants to move back to the centre, so the force is negative. So what we would say is that the restoring force is directly proportional to the displacement from equilibrium. The further away from equilibrium, the larger the force. At equilibrium, there is no restoring force. Now, this also means that the greater the displacement from the equilibrium position, the greater the acceleration experienced by the object. So what we would say is that simple harmonic motion can be defined as an oscillation in which the acceleration of an object is directly proportional to its displacement from its equilibrium position and is directed towards the equilibrium. Now, this can be represented with the equation A is directly proportional to negative x. Now, if any equation contains this relationship, the object must be undergoing simple harmonic motion. Now, this is like an object carrying out circular motion. The centripetal force always acts towards the centre of rotation. Now, the centripetal force, literally meaning centre-secant force, is always acting towards the centre of the rotation. This therefore means that the centripetal acceleration acts towards the centre of rotation, the same direction as the centripetal force, because according to Newton's laws of motion, acceleration is always in the same direction as the resultant force that causes it. Now, it could be considered that the force and acceleration are trying to make an object move back to the equilibrium position of the motion, the centre. Now, we can consider an object carrying out simple harmonic motion, which is an object that's oscillating backwards and forth in the same plane. Now, in Newtonian mechanics, you can decide which direction is positive and which direction is negative. So it is up to you fundamentally in which way you're going to suggest it's going to be a positive motion and which way it's going to be a negative motion. Now we define in this motion that the equilibrium position as the midpoint in the oscillation. So the equilibrium position is the position where the pendulum would hang if there was no force placed upon it. The equilibrium position of an oscillator can be found by letting the object hang freely. Now the restoring force in simple harmonic motion always acts towards the equilibrium position. This is always acting in the opposite direction to the displacement, as shown in the following image. Now in circular motion, the resultant force always acts towards the centre of the rotation, and in simple harmonic motion, the resultant force always acts towards the centre of oscillation, the equilibrium position. So, the restoring force of simple harmonic motion is equivalent to the centripetal force of circular motion. So the restoring force of simple harmonic motion and the centripetal force of circular motion both wish for the object to reside in its lowest possible energy state. The restoring force does not keep an object an oscillating motion at equilibrium due to inertia, whilst the centripetal force does not keep an orbiting object at the centre of the rotation due to inertia. Now, this shows us that simple harmonic motion and circular motion obey the same laws of physics. The only difference is each motion has a different reference point for its centre of motion. And it shows us that simple harmonic motion and circular motion are both derived from Newton's laws of motion. They are the same physics principle from different frames of reference. So, if we displace an object in simple harmonic motion by a displacement of x, there'll be a force that will bring the object back to the equilibrium point. We call this the restoring force, and it always acts in the opposite direction to the displacement. We can represent this mathematically as this restoring force is proportional to the negative displacement. Now, as we know, F equals ma and the mass is constant in this system. Now this can also be written as therefore A is directly proportional to negative x. Now the minus sign implies that the restoring force and the acceleration acts in the opposite direction to displacement. So for example, if the object is displaced left, the restoring force and the acceleration act to the right. So F being proportional to negative x indicates that the restoring force is directly proportional to the displacement from equilibrium acting in the opposite direction. And A being proportional to negative x indicates the acceleration produced by the restoring force is directly proportional to the displacement from equilibrium acting in the opposite direction. Now either equation can be stated as the condition required for an oscillator to be acting as a simple harmonic oscillator. So, for an object to be moving with simple harmonic motion, its acceleration must satisfy two conditions. Firstly, the acceleration is proportional to the displacement. And secondly, the acceleration is in the opposite direction to the displacement, towards the equilibrium point. So we can consider the acceleration in simple harmonic motion to be a restoring acceleration, as it always wishes to bring an object back to the equilibrium position. We're now going to consider the equations of simple harmonic motion by looking at the motion of a simple harmonic oscillator. Now to fully analyse this motion, we must consider one cycle of a pendulum or any oscillating mass. In this example, we've defined left as negative displacement and right as positive displacement, but this is arbitrary. Now one cycle of the simple harmonic oscillator is the equivalent to one cycle of a wave or one rotation of circular motion. This indicates to us that the phase difference of one cycle is equal to 2 pi radians or 360 degrees. Now different oscillators can have different phase differences as shown in the following animation. Now oscillators can have a phase difference which is how much the oscillator will lag behind another oscillator. Now back to this definition of a cycle. We define one cycle as the pendulum bob being displaced in the negative direction at point 1. It is then released and swings through point 2 at its maximum speed until it reaches point 3 when it comes to a complete stop. It then swings to the negative direction, reaching a maximum speed at point 4. It then completes a full cycle when it stops at point 5. Now, at point 1, the pendulum has a maximum displacement in the negative direction. Now, as we said before, one cycle is the motion of the pendulum to return to its original position of maximum displacement. Point 2 is that the pendulum has a zero displacement from the equilibrium position. Point 3, the pendulum has maximum displacement in the positive direction. Point 4, the pendulum will have a zero displacement from equilibrium. And at point 5, the pendulum has a maximum displacement in the negative direction. Now this is one complete cycle for an oscillator. Now, if we consider the pendulum being displaced by a displacement of x as shown in the following image, amplitude A is the maximum possible displacement from equilibrium for that object. Now we think in this example the pendulum starts its motion at maximum displacement A, the amplitude. As the pendulum moves to the equilibrium position, its displacement is zero. When it moves to the maximum displacement in the opposite direction, it's negative A. Back to our equilibrium position, again its displacement is zero. Now at this point the body has inertia, so we'll keep moving past the equilibrium position. Then the pendulum will return to its original maximum displacement, the amplitude A. So we can summarise this information with the following diagram. Now, if we consider the displacement of a simple harmonic oscillator against time, we would get the following graph. Now we can express the x-axis of this graph as either time or angular displacement. Now because this is a cosine graph, it means that the cosine function must be present in the term to describe displacement. So what we would say is that the displacement of bob x after time t is given by the equation x is equal to a cos omega t, which is equal to a cos 2 pi ft. Now since f is equal to 1 over t, then this equation can become x is equal to a cos 2 pi 1 over t times by t, so therefore it equals a cos 2 pi small t over big T, where small t is the time into the cycle the oscillator is, and big T is the time taken for one complete cycle. This means that as the object displaces more and more, cos 2 pi t over t becomes closer to 1. Now this equation does use the small angle approximation, so we've got to use radians when we calculate values with cosine. Now this equation therefore is only true when the angle of displacement from the oscillator is 10 degrees or less. So this equation assumes that the object has started to oscillate from the maximum displacement position. If the oscillator starts oscillating from the equilibrium position, another form of the equation must be used, and that is x is equal to a sine omega t, or a sine 2 pi f times by t. This is because a cosine graph starts at a maximum, whilst the sine graph starts at zero. So to clarify, to work out the displacement when the oscillator starts its cycle at equilibrium, we would use x is equal to a sine omega t, whilst the displacement when starting from the maximum displacement is x is equal to a cos omega t. The correct equation to use is dependent on the starting conditions of the oscillation or the phase of the oscillation. So if the object begins oscillating from its equilibrium position, then at time is equal to t equals 0, the object is at its equilibrium position and its displacement is 0, so we must use the sine version. If the object begins oscillating from its amplitude, then at time t equals 0, the object is at its positive amplitude, so we've got to use the cosine version. So you can see this in the following graph shown here. For a mass on a spring oscillating from t equals 0 at equilibrium, and a mass on a spring starting oscillating at t equals 0 at maximum displacement. Now considering the displacement of a simple harmonic system shows the link with circular motion stated earlier in the following animation. Now we can calculate the phase difference between two oscillations in simple harmonic motion. The phase difference is the angular difference for the displacement between two successive oscillations, which is shown in the following animation. Now the phase difference between simple harmonic oscillators is equal to 2 pi small t over big T. Our unit of phase difference in this concept will be radians, and this only works when the oscillations have the same frequency or wavelength. The objects are coherent oscillators. Now the phase difference can be considered the difference in swing cycle between two pendulums. So the phase difference can be worked out by comparing the displacement time graphs of different simple harmonic oscillators, as shown in the following image on the screen. Now two identical pendulums oscillating in step both reach their maximum positive displacements at the same time. Their phase difference is 0 radians and they are in phase. If they are in anti-phase displacement, a phase difference of pi radians, one pendulum will be at its maximum positive displacement and the other pendulum will be at its maximum negative displacement. So if we go back again to considering our pendulum being displaced by x, we can now look at the velocity of the pendulum during this motion. When we start off at a displacement of negative x, the pendulum starts its motion at the maximum displacement a, its amplitude, and at this point the velocity is 0. This is because at this instance it's not moving. When we get to our displacement of equal to 0, the velocity is a maximum. Because as the pendulum moves through the equilibrium position, the velocity is at its maximum value. This is because there's no longer a restoring force on the object as it's in equilibrium. This means that due to F equals ma, there is no acceleration on the object. However, the object continues to move through equilibrium as it has inertia at this point. Then, when we've got a displacement of x, once again, the velocity is equal to 0, because at this instance, the object has stopped moving. Once again, we go back to equilibrium position, the displacement is 0, the velocity is a maximum, because there's no more restoring force or resultant force acting on our object at this point. But again, the object will continue to move through equilibrium as it has inertia at this point. The pendulum then returns to 0 velocity at its maximum displacement at the start of the cycle. So we can see here on our following diagram that when you have maximum displacement you have minimum velocity, and when you have minimum displacement you have maximum velocity. Now the velocity of the bob at displacement x is given by the equation v is equal to plus or minus 2 pi f or omega times by the square root of amplitude squared minus displacement squared. Now the plus or minus sign represents the oscillating motion of the pendulum. Now the maximum velocity occurs in the middle of the swing when we said that the displacement is 0, so x will equal 0. So as you can see here, we can work it through to get v is equal to plus or minus 2 pi f times by a. Now this is the maximum possible velocity for the object, and again the sign, the plus or the minus, depends on the way in which the object is moving in the cycle. Now if we consider again a pendulum displaced by x, we can now look at the acceleration of the pendulum during this motion. So again, if we have a displacement of negative x, the acceleration is at a maximum, because what we can say is that the resultant force and acceleration are proportional to the displacement. However, remember, the force and the acceleration act in the opposite direction to the displacement. When the pendulum bob hits equilibrium position, we know its displacement is 0 and its acceleration is also 0. Because as the pendulum moves through the equilibrium position, that will be the case, because as we said before, the resultant force and acceleration are proportional to the displacement. No displacement, no acceleration. When we get to our displacement of x, our acceleration is a maximum again, because we have a maximum displacement, because our resultant force and acceleration are proportional to the displacement. Once we go through our equilibrium position again, the displacement and acceleration will both be 0, because there's no displacement, so there's no acceleration. We then return back to our original position of minus x, and here we've got our maximum acceleration again, but remembering that the acceleration is in the opposite direction to the displacement. So we can summarize that when we have a maximum displacement, we have a maximum acceleration. When we have a minimum displacement, we have a minimum acceleration. The displacement and acceleration are always proportional to each other, but in opposite directions. Now this is indicated as one term has a positive value and the other term will have a negative value. The velocity of the oscillator is always the opposite compared to the displacement and the acceleration of the oscillator. So if you've got a maximum velocity, you'll have a minimum displacement and acceleration. Now, the acceleration of the bob at displacement of x is given by the following equation. Now always remember, the acceleration acts in the opposite direction to the displacement. So we can say a is equal to negative 2 pi f squared times by x, or a is equal to minus omega squared times by x. Now this indicates that this is simple harmonic motion. At these equations we can say a is proportional to negative x. So therefore, we can then say that the maximum acceleration occurs at the ends of the swing when the displacement is equal to the amplitude. So x is equal to a. That's because when the displacement is 0, the acceleration is also 0 because there's no restoring force. when the displacement is a maximum, the acceleration is a maximum because there is a maximum restoring force. So our maximum acceleration produced by the simple harmonic object is going to be A is equal to minus 2 pi f all squared times by A, or minus omega squared A. So, as I've said before, we know that A is equal to minus omega squared x. So this indicates that the proportionality constant between A and x must be considered to be omega squared. Now we can graph this as the following. Now, since the gradient for a particular oscillator has to be constant, this implies that the frequency and the period of the oscillator is also constant. Now, an important aspect of simple harmonic motion is that the period of the oscillator is independent of the amplitude of the oscillator. So as the amplitude increases, so does the average speed of the swing. So the period of the period does not change. Now, such an oscillator is referred to as an isochronous oscillator. So here we have a summary of the simple harmonic motion equations. That the general displacement equation is x is equal to a cos omega t or a sine omega t. The maximum displacement is x is equal to a. The general velocity is v equals plus or minus omega squared times by the square root of a squared minus x squared. On the maximum velocity is v is equal to plus or minus omega a. The restoring acceleration is a is equal to minus omega squared x in general, or for the maximum value, a is equal to minus omega squared a. Now remember, our restoring acceleration equations give us the condition of simple harmonic motion. The equation we can see up here is the equation used to work out the displacement from equilibrium at a particular time in the motion. This equation is used to work out the maximum possible displacement from equilibrium, the amplitude. This equation is used to work out the velocity at a particular time in the motion, whilst this equation is used to work out the velocity at the equilibrium position in the motion. And like we said here, these equations can work out the acceleration at any point in the motion, whilst this can work out the acceleration at maximum displacement. So to summarise what we've learnt in today's lesson, we've looked at displacement, amplitude, period, frequency, angular frequency and phase difference. Angular frequency is equal to 2 pi over t, which is equal to 2 pi f. Simple harmonic motion without defining an equation is a is equal to minus omega squared x. The solutions to the equations, including x is equal to a cos omega t or x is equal to a sine omega t, then velocity is equal to plus or minus omega times by the square root of a squared minus x squared, and the maximum velocity is equal to omega a. So if we've been successful and we've learnt in today's lesson, we should be able to describe the characteristics of simple harmonic motion, explain the conditions needed for simple harmonic motion, and calculate properties of simple harmonic oscillators. So thank you very much for watching this lesson on simple harmonic oscillators, which is part of the oscillations topic in the Module 5 Newtonian World and Astrophysics for OCR A-Level Physics. Thank you so much for listening and have a lovely day.